Hello everybody and welcome to my talk. My name is Emil Bronstein. I'm from the Technion, Israel, and I'm going to present our work on the analysis of austenite-martensite phase boundary and twin microstructure in shape memory alloys, while our emphasis is going to be on the role of twinning disconnections. Let's begin with a little bit of motivation. We can see the microstructure illustrated here during a phase propagation. And we can see the habit plane, denoted by the red line, that separates two different phases, the austenite on the right from the martensite on the left. Far from the habit plane, we have a single martensite area, denoted by M2, and in between we have the twinned microstructure, composed of alternating martensite twin variants, denoted by M1 and M2. When they are separated by the blue lines here, which are the twin boundaries, or TBs. Two more notations we have in this illustration is the coordinate xi, which is the coordinate along the twin boundaries from the habit plane. When xi equals 0, we are exactly at the habit plane. And we also have lambda, where lambda is the twinning periodicity, or in other words, it is the width of two adjacent martensite twins. Now, in this microstructure, we can zoom in or take a look at the vicinity of the habit plane, and we can see here that there is a fundamental incompatibility between the unit cells of the austenite and each of the martensites. Due to this fundamental incompatibility in the unit cells, an elastic energy is introduced to overcome this strain incompatibility. Now, this elastic energy is concentrated at a small layer of width of approximately lambda close to the habit plane, and this elastic energy is proportional to lambda. On the other hand, due to existence of twin boundaries in our microstructure, we have the twin boundary energy, UTB. And this twin boundary energy is composed of gamma TB, where gamma TB is the interfacial energy per unit area of a flat twin boundary, and it is a material property. Now, this twin boundary energy scales with the density of the twin boundaries, or in other words, it is proportional to 1 over lambda. So on one hand, we have an energy term which is proportional to lambda, and on the other, we have energy term which is proportional to 1 over lambda. So we can sense that there is some sort of competition here between these two energy terms, right? The elastic energy prefers small lambda close to the habit plane, while the twin boundary energy prefers large lambda in the entire twinned microstructure. So we ask ourselves, what would be the lowest energy solution? And the lowest energy solution would be to have small lambda close to the habit plane and let it grow with the distance from it. Now, we've understood from energetic point of view why this is the best solution or the lowest energy solution, but we can actually back this logic up in experimental observations such as these. We can actually see the twinning periodicity lambda, or the width of two adjacent martensite twins. We can see how small it is and fine it is close to the habit plane, and becomes coarser and larger with the distance from it. Now we ask ourselves, how can lambda vary? And the answer to this question would be twinning disconnections, or TDs. Now, a twinning disconnection is a line defect that is characterized by a Burger's vector B, a step height h, and an energy per unit length gamma TD. Now, the twinning disconnections are the topological features that enable the deviation of twin boundaries from their twinning planes, or from their energetically favored planes. And both gamma TB, which is the interfacial energy of a flat twin boundary, and gamma TD, which is the energy of a twin in disconnection, they both play a major role in nucleation and propagation of twin boundaries as illustrated in this image. Therefore, they are significant to processes such as twinning and detwinning, and of course to phase transformation and phase boundary propagation. Now, these two energies are atomistic scale properties that cannot be measured directly, and despite their major role in transformation kinetics, there are only few rough estimations of these properties in SMA in the literature. Now let us take a look at this microscopic image that was captured in our lab during a study of a phase transformation of a nickel manganese gallium single crystal. And we can see the features that were illustrated above. We can see the habit plane that separates the austenite from the martensite, and of course the microstructure. And we can see how fine the lamellar microstructure is close to the habit plane. And we already established that this is associated with the elastic energy. We can actually see the twin boundaries, which are these lines that separate martensite or adjacent martensite twins, which are the bright and dark stripes, in this image. But maybe the most interesting features to see would be the annihilation of twins and a variation in lambda. Now let us zoom in on this magenta rectangle and observe these features. We can actually see how twins, for example this one, the dark stripe, how twins are annihilated. This twin is annihilated approximately at this point, this one at this point, and at this point. So we can actually see how twins are annihilated, how twin boundaries deviate, and how lambda, which is small here, becomes much larger here, or grows with the distance from the habit plane. Now we can understand that there are total of three major contributions to the total energy of this unique microstructure, which are the elastic, the twin boundary, and the twin and disconnection energies. When these material properties, gamma TB and gamma TD, are the properties we would like to evaluate. And how are we going to do it? Using the following recipe. First, we will express all energy terms analytically. Then we will minimize them with respect to lambda of Xi, when lambda is the twinning periodicity and Xi is the direction along the twin boundary from the twinning plane. Simultaneously, we can perform analysis of microscopic images to obtain lambda, to which we can fit theoretical expressions, eventually leading us to extraction of the desired material properties. Now, in the development of the analytical models for the twin boundary and twin disconnection energy, we've made a few assumptions. On the same twin boundary, all twin disconnections have the same sign in theory of dislocation notation. Or in other words, they all repel each other, they all contribute to the deviation of the twin boundary, to the same deviation of the twin boundary from its twinning plane. And most of the twin boundaries have multitude of other twin disconnections. Most of the twin disconnections have multitude of other disconnections from each side, and they are mainly affected by the closest ones. Thus, we conclude that the distance between adjacent twin disconnection is constant. And this leads to a constant slope of d lambda d Xi. Or in other words, lambda, the twinning periodicity, is a linear function of the coordinate Xi with the constants lambda naught and k. Okay, now that we have lambda and we assumed that lambda varies linearly with the distance from the habit plane, or lambda is a linear function of Xi, we can develop these two energy terms for the twin boundary and twin disconnection energies. And for those of you who are interested to see in the development of these terms, you're welcome to see it in our paper. Now, We did not rely only on the explanation in the previous slide that explained the linear relation between lambda and xi. We took a step forward and actually measured this relation. And we can see that the measured data between lambda and xi indeed displays a linear trend to which we could fit a linear fit and evaluate the parameters lambda naught and k. So now that we have actual values for lambda naught and k, we can minimize the total energy of this microstructure with respect to these parameters, to lambda naught and k, substitute their measured values, and eventually extract our desired material properties, gamma Tb and gamma Td. We note that in our developed models, both gamma Tb and gamma Td are a linear function of the elastic modulus E. Now let's say a few words about the obtained results. Regarding gamma Tb, we can say that it is actually in a good agreement with previous study in this reference that was performed also on a nickel manganese gallium single crystal, very similar to our studied material. On the other hand, we found no previous studies that reported the value of gamma Td in nickel manganese gallium. And to the best of our knowledge, there is no reported value of gamma Td regarding any shape memory alloy whatsoever. So we wanted to compare this result to something, and we decided to compare it to two known cases from the theory of dislocations. The first case would be gamma edge, which is the energy of a single edge dislocation, and the second case would be gamma pileup, which is the average of a single dislocation in a pileup. Now, we note that in our developed model, gamma Td is a linear function of E, but also in the models appearing in the theory of dislocations, gamma edge and gamma pileup are also linear functions of the elastic modulus E. And this is very good. Why? Because we found differences of a factor of up to 3 in the reported values of the elastic constants of nickel manganese gallium. So the fact that these energies are all functions of E gave us the ability to compare their proportionality factors, or compare these energies divided by E, thus eliminating the uncertainty of the choice of E. And actually we obtained a great result. Our result is bound by two known cases from the theory of dislocations. And let's explain these bounds. We can see that our result is higher than the energy of a single edge dislocation. And it makes sense, because this single edge dislocation is an isolated one, while in our case a single twin disconnection interacts with other disconnections, thus we expect its energy to be higher. On the other hand, our obtained result is lower than the average energy of a single dislocation in a pileup, and this also makes sense due to the strict boundary conditions of this pileup compared to the boundary conditions of our case. So, if to summarize and conclude, we model the role of twin disconnections in the twin microstructure in the vicinity of the phase boundary. We extracted the twin boundary and twin disconnection energies in nickel manganese gallium single crystal, which are atomistic scale properties that cannot be measured directly. And to the best of our knowledge, the twin disconnection energy has no reported value in the literature regarding SMA whatsoever. And on top of that, we bounded the energy of the twin disconnection by two known cases from the theory of dislocations. Thank you very much for listening.